Dr. Jiaqi, are you there?
Yes, I'm here.
Okay,
Can
great. Welcome back to the second session in the afternoon. So this topic will be security, reliability, and privacy. So Dr. Guo, yeah, please go ahead.
Yeah, sure. Hello, everyone. Welcome to our second section about security, reliability, and privacy. My name is Jiaqi from Xi'an University. I'm on behalf of Ming to host this section. Okay, we have 4 research papers in these sections, and we got 90 minutes in total. That means each speaker can have at most 20 minutes to present and answer the questions from audience. Now, I would like to invite the speaker, Messe, of the first papers, an access-based assistant for security by design. Messe, are you in this section? Okay, great. I can see your screen here. But
Hi, can you hear me?
Yes, now we can hear you.
Okay, thank you.
Yes, sure.
So can I start?
Yeah, please go ahead.
Hi, thanks for attending to my presentation. My name is Messe, and I'm working at the laboratory IRISA in France. Today I will give a presentation on the paper titled Asset-Based Assistance for Secure by Design. So first of all, let's look at some statistics. According to Symebase, there is a cyber attack every 39 seconds, and 43% of them target small-scale organizations. Over 75% of the health care facility has been infected by malware in 2018, and approximately $6 trillion is expected to be spent globally on cybersecurity by 2021. So as we can see, the security aspect is important in today's software development, and the security cannot be added as an afterthought, or it will cause serious financial damage. So we can say that secure by design is necessary, which means that integrating the security aspect since the early phases of the software development lifecycle is extremely important. So in this paper, we focus on integrating the security at the design phase. At the design phase, the role responsible for designing a software system is called an architect, who is knowledgeable about the system architecture design, but he or she may not always well trained in security. So they may need some help from the security experts if they want to design secure architecture solution. But there is a knowledge gap between architects and the security experts because there is a lack of shared terminology for the characterization of cybersecurity. For example, there are some security jargons that are often used by security experts, such as XSS, CRSF, etc., which may not be easily understood by architects who have limited security knowledge. Another problem is the high variability of applicable threats over time. With time passing, there are many different forms or techniques of attacks, depending on the system deployment context and on other aspects. So to design a one-size-fits-all solution is not so easy. So the architect may need help from security experts, but involving security experts is not always possible due to time to market and budget constraints, especially to small-scale companies. Some other solutions are such as security modeling languages are proposed, such as UML-sec and Secure UML. But their utilization also requires some minimal security expertise. So in this paper, our objective is to provide security assistance to those architects who have limited security knowledge in order to integrate the security aspect into the architecture model at the design phase. For that, we have to include some security knowledge into our security assistance, such as vulnerability, threat, and attack information. And at the end, this security assistance will be able to alert the vulnerable parts in the architecture model and also recommend the security control solutions. So our security assistance will have to include some minimal security knowledge. At least 3 security information have to be included. Their attack, vulnerability, and security control or mitigation information. This information are necessary. For that, we will take use of some current security repositories, which are promoted by MIT organization. For example, for the attack information, we will use GABEC repository. So GABEC is a common attack pattern, enumeration, and communication. And for the vulnerable information, we will use common weakness enumeration, which enumerate the weakness information. And for the security control, we will use both GABEC and CWE, because for each attack pattern and for each weakness, GABEC and CWE provide corresponding mitigation information. So we can take use of both of them. So that was for the security information. And as we deal also with architecture elements, we will need a standard naming scheme to represent architecture elements. For that, we use common platform enumeration, which is also promoted by MIT organization. So it is worth noting that all the above repositories are maintained by MIT, and they are frequently updated and widely used by the security community. And GABEC, CWE, and CPE are related to each other. For example, an attack pattern in GABEC is related with several weaknesses in CWE. Now let's see our approach. So the foundation of the security assistance is based on a novel refinement of the asset concept. As our goal is to bridge the 2 universes, so the architecture modeling universe and the security universe, we will have to find a bridge, which we believe that the asset is this bridge. Here we propose a novel refinement of asset because we find that the actual definition of asset is pretty vague and flu, and it is defined by ISO as anything that has value to organization. So we can see that it is a pretty vague definition. In our situation, as we try to bridge the 2 universes, or we can say that we bridge the 2 different points of view. So we refine the asset into different refinement to represent asset from different viewpoints. For example, for domain expert or for architect, we have defined the domain assets. They are domain asset is anything that has value for domain experts or architect towards the fulfillment of the function and the goal of system, together with the assurance of its properties. On the other hand, we define vulnerable asset, VA, as anything that has value for security experts. So it has vulnerabilities that can be menaced by threats. So domain asset and vulnerable asset present the 2 universes, and to bridge them, we will project the common vulnerable asset into the architecture model, so into the domain asset, and we obtain, so this green part, the vulnerable domain asset. So vulnerable domain asset is anything that has value for not only domain experts, but also for security experts, because it has vulnerabilities that can be managed by threats. So the goal of our assistance is to identify these vulnerable domain assets. Like that, we can find the relevant asset or architecture element that we have to deal with their vulnerabilities. And after, we can propose the relevant security controls. Based on this novel refinement, we propose an asset-based three-view security assistance framework. So as we can see, at the left and the right, we have the information from the two universe, and our security assistance use vulnerable domain asset to bridge the gap and propose and recommend security controls. So at the left part, under the viewpoint of architect, so this architect will have to annotate it on the architecture element that he or she wants to protect, and annotate about the security property and category information. Like that, in fact, this annotation is equivalent to a security requirement. For example, if there is a database server as an architecture element in the architecture model, the architect can annotate on it the data confidentiality. So the data is the category and the confidentiality is the security property. So this together, this security requirement will be the input of our assistance. At the right side, in our security assistance knowledge base, we have collected the common vulnerable assets, which are domain independent. These vulnerable assets are retrieved from GAPEC and CWE and other repositories. And to link the domain asset and the vulnerable asset, or we can say to pass from domain dependent knowledge to domain independent knowledge, we use only the category and the security property information. So in our example, the data confidentiality is this link. And when we have the data confidentiality, we will search in our knowledge base the compromise of which vulnerable asset can impact on data confidentiality. For example, in our knowledge base, we have a vulnerable asset called untested SQL input. So if its vulnerability is exploited, the data confidentiality will be impacted. In this way, we find finally a list of vulnerable domain assets, and according to security repositories, we can propose the relevant security controls. So to allow the enactment of our security assistance, we have designed a data model, which includes the necessary concept and their relations to achieve this security assistance. As we can see, there are 4 different parts colored with different color in this domain model, and each part includes information from a viewpoint. For example, the blue part represent the domain architecture modeling, such as the architecture element, etc. And the green part represent the attacker's viewpoint, such as attack vulnerability types, etc. And the red part represent the security assistance viewpoint. So we can see here at left, we have annotated domain assets. At right, we have vulnerable assets. And our assistants make link between them by using vulnerable domain assets. And all these 3 assets are connected by the general element types. So more details of this data model can be found in the paper. Here, I just pass to the next. For the enactment of our security assistance, we have also proposed a BBMN-based process. As we can see, there are two main parts. A part includes architect's annotation tasks, and another part includes the security assistance tasks. So in the security assistance part, there are four main steps. Firstly, according to the architecture elements, we select relevant element types. In parallel, we select security information such as vulnerable asset, and then we make a matching between element types and the vulnerable asset. That's how we bridge the two universes. Based on this matching result, at the end, our security assistance can return security control solutions. And we also have implemented the above knowledge into a web application prototype tool that can be used by architects who are security novice. As we can see, this is the homepage of the prototype tool. We need three information that can be considered as a security requirement. So the input of our security assistance. And the architect will need to select an architecture element that he or she wants to protect during the architecture modeling, and annotated a security property and category. Like that, our assistance will return information about the vulnerable domain asset together with their vulnerabilities and security controls. So all this information are retrieved from common security repositories. So now here comes the conclusion. In this paper, we have proposed an asset-based security assistance to ensure security by design. For that, we have proposed a novel refinement of the asset concept, which we consider as a bridge to represent different viewpoints. Based on this novel refinement, we have designed an asset-based three-view security assistance framework. More precisely, we have designed a data model and a BBMN-based process to allow the enactment of this security assistance. And we have also shown that it is possible to define this security assistance by implementing our approach into a web application prototype tool. In the future, we have to validate the effectiveness and usefulness of this security assistance by conducting a crossover experimentation, which is ongoing work in our university. And another main perspective is that we are aiming at automating the security knowledge extraction, such as vulnerable asset extraction from existing security knowledge base and its insertion into the assistance database. So that's all for the presentation. And thank you for your listening of my presentation. And I'm opening to receive all kinds of feedback. And I'm also search possible collaboration if you are interested in the security by design domain.
Thank you for a great presentation. Do anyone have any questions about this work? Okay, then I have one simple question about this. Can you briefly introduce the major challenges in matching assets and vulnerable assets?
To matching, you mean matching the domain asset and the vulnerable asset, right?
Yeah. Once their architects define the security property and their and the elements in their architecture, and then how the assistant to match this information to the to the one defined by the security expertise.
Yeah, it's really a good question because it's another perspective of our paper. In fact, now what we do is totally manually matching. So for the matching, we have two directions. One is the syntactical matching. So we just look at the strings. And another is the semantic matching. For the semantic matching, we are trying to use a tool for this, which is called S-match, which allows to learn the concept and trying to match semantically. For now, and for the syntactical matching, now we are using common platform enumeration because this is a platform who provide a standard naming scheme for different platforms, and this allows us to do the syntactical matching. So this the two future directions to try to automate this matching process. For now, at the current state of the paper, this task is conducted by the authors, so manually, and it's not totally automated.
Okay, and I got it. Thank you for your presentation.
Okay, thank you.
Okay, now let us invite the second speaker, Duoyuan of the papers, a knowledge graph-based sensitive feature selection for Android malware classifications. Okay, we can see your screen now. Duoyuan, you can begin now. Yes, Duoyuan, we cannot hear your voice and see your screen here. Do you have any problem? Hi, Ningning, are you there? Are you in this section? Okay. Duoyuan seems to have some problems in his microphone. Ningning or the Bakheet are in this section. So, would you like to begin your presentation first? Okay, thanks, Ningning. Let us invite the speakers of the third paper, Modeling and Verifying Data Access Mechanism of NLSR Trust Model. Ningning, you can share your screen here.
Yes.
Oh, we can see it.
Okay. Can.
Sure. Please go ahead.
Hello everyone, my name is Chen Ningning. It's my great honor to introduce my paper Modeling and Verifying Data Access Mechanism of NLSR Trust Model. I will describe this paper from the following 6 sections. The first one is the introduction, then overview of data access mechanism of NLSI, modeling data access mechanism of NLSI. The third one is verification, improvement, and conclusion. The first one is the introduction. According to existing studies, NLSI is proposed as an intra-domain routing protocol for NDN. There are still a lot of security issues in NLSI data access mechanisms, such as the fake and the leakage of data. So that we formalize NLSI data access mechanism by using CSP communication sequential processes. We applying PET, we verify for vital properties, including data freedom, data security, data decryption, and data availability. According to the verification results, the results, the trust model counter protects the data from leakage and fake once intruders appear. So we improve the model by using a method which is similar to digital signature firstly. To further accelerate the key fetching and verification process, we use a special packet to package information for multiple keys, which name is key bundle. Okay, the next part is the overview of data access mechanism of NLSI. In this, we give a 5-level trust model. In this figure is used to ensure the security of NLSI. The top is root key, site key, then operate key, root key, then NLSI key, and disk key. The detailed is described in this paper. Please read the paper for details. Okay, the next one, this scheme contains the following entities: reader, writer, handler, router, router I, router W, link state database, LSDB, and intruders. Writer modeling is made up of writer, router, W, handler, LSDB, and intruder. Reader modeling is made up of reader, router, handler, LSDB, and intruders. Figures describe the inter-processes communication between processes. Okay, when a reader obtains a data packet, the following sequence of actions occurs. Step 1, at first, a reader sends the required data name DN to a router. Then, step 2, the router replies the reader data packet containing data decrypted by an NLSR private key, and the key locator is NPK. The key locator guides the reader to get the corresponding NLSR a key object NPK from the router. The router transmits an interest to obtain NPK. The reader receives NPK from the router. Then the reader verifies NPK using verification process. If the reader needs other key objects, then we go to step 5. Otherwise, the process terminates. The reader gets key objects of the original router IPK by sending LSDB an interest. LSDB replies the reader a packet IPK. Similarly, the reader decides whether to go to the next step. Next step or terminate, which is based on the validation of IPK. The reader requests an operator's key object, PPK. PPK is sent to the reader. The reader chooses to go to the step, the next step or terminate on the basis of the validation of PPK. The reader asks for a size key object SPK. The reader asks for a size key object SPK. LSDB returns SPK to the reader. The reader chooses whether to obtain NPK on the ground of the validation of SPK. The reader sends the name of root's self-signed packet APK to LSDB. The reader obtains router's self-signed packet APK from from LSDB. The reader has got all key objects corresponding to the 5 levels of trust model. By using verification process, the reader can consume and store all related packets. The process of producing data is defined similarly. Please read the paper for details. When a receiver gets a packet, it starts to verify the packet. The verification process is described as follows. Then we talk about it. Step 1, a receiver checks the key locator files. If the file contains a case name or the root's public key, the receiver goes to step 2. Otherwise, the receiver can't decrypt the packet successfully and drop the packet. Step 2. If key locator is the key's public key or one of a known and previous verified case name, the process goes to step 3. Otherwise, the process goes to step 4. Step 3. Receiver decrypts all packets from top to bottom of the trust model. The receiver can't decrypt all packets. We can find out the first packets that can't be decrypted successfully. If all packets can be decrypted, the receiver checks whether the packet is our desired one and store related packets. Step 4. Key locator is a name of an verified key. The receiver forwards a new interest packet to obtain the key objects. Step 5. receiver gets another packet corresponding to the key locator. Then the process recursively executes step 1 to 5. The next part is the modeling data access mechanism of NLSI. These people define the CSP model system W and system I without intruders. System W represents the process of producing and providing data. System W contains LSDB writer, router W, and handler. LSDB system I is made up of LSDB reader, router I, and handler. To take intruders into consideration, we create a system WI and system II based on system W and system I respectively. For simply, we only introduce the detailed modeling process of reader here. Readers request a data packet and verify signature of the data packet. We formalize a process read their rules without intruders, shown in this. In order to simulate internal processing, we use process handler to address decrypting packets and to check the decrypted packets. We only give an example. Handler 1 is used to represent the situation where only 2 packets are used for decryption. This process is defined to accept process results from internal process handler. These people models read with renaming read I0 to take intruders into consideration. The subtraction builds intruder process. Intruder can intercept or fake message in the communication with channel get date COMMI and COMWI, shown in this. The next part is the verification. In this section, we use model check PET to verify 4 properties, including data freedom, data security, data decryption, and data availability. The first one is the data freedom. System should not run into a deadlock state. In PET, there is a primitive to describe this situation. The next one is data security. Data security. In addition, the leakage of data will produce better effects using average operator. We define using operator, we define this assertion to guarantee that intruders can't obtain the data at any time. The third one is data decryption. If the key locator of the packets is changed, the packets can't be decrypted successfully. Therefore, the assertion is given to guarantee that the decryption process is always succeed. The last one is data availability. The last assertion can guarantee that data is finally available for entities by using inventory operate. Without considering the intruders, all properties are valid for system I and system W shown in this figure. When we take intruders into consideration, the verification process of 4 properties I show in this figure. Property 1 is property 1 deadlock freedom is valid. This means that the model can't run into a deadlock state. Property 2 data security is invalid. This represents the intruder can't obtain data. Property 3 data decryption is invalid. with the intruder's intervention entities counter decrypt data packets successfully to obtain their desired date. Priority 4 data availability is invalid. This shows that entities can't get desired data with the intruders. The next part is improvement. In order to ensure this model to satisfy priority 2, priority 3, and priority 4, we input this model by using a method which is similar to digital signature. Then we change at first we change message date 2 to message date 2 1 and message int to message int 1 respectively. The content and the key locator of the packets are encrypted by a public key. The packets must be decrypted by using the corresponding private key. To introduce the first input model, we give an input version named read 01 or read 0 as follows, showing this. The verification results of all properties are valid for this first input model. We make the first improvement model more efficient by using key bundles. A key bundle corresponds to a data packet, and the packets or keys used in the verification of the data packet. We give an improved version named router I02 of router I01 to describe the second improved model improvement. This paper verifies the priority 3 data decryption by applying the first improved model and the second one respectively. We compare them in validated state, total transaction time, and memory used. The results mean that the second improved model is more efficient. And finally, we conclude this paper. We have formalized the data access mechanism of NLSR using CSP. By applying patch, we verify the model. The properties, data security, data decryption, and data availability are invalid with the appearance of intruders. Then we input the model with a method which is similar to digital signature. To further accelerate the key fetching and verification process, we use a key bundle to package multiple keys. Thank you very much.
Thanks for your great presentation. Yes, I have a similar question about the soundness and the completeness of the modeling. How do you verify and examine the soundness of the modeling of your modeling about the NLSR protocol?
Okay, let me see. Let me say at first let me say it. Let me say it first. We choose communication sequential process as our formal language. Then we can see this. You can see this. This is described by CSP. Then this is the reader modeling is described by CSP. Then by applying model check patch, we formalize the we verify the CSP model. Then by using LTL formalize we describe we give their assertions to describe data freedom, data security, data decryption, and data availability. In this, then we have the results. Okay.
Okay, sure, I get it. Yeah. Okay, thank you again. Thanks again for your great presentation and your great work.
Oh, okay, thanks.
Thank you.
Thank you.
Okay, now seems Yuan seems solved his microphone problems, and now we welcome Yuan to present his work about to give his work about a knowledge graph-based sensitive feature selection for Android malware classification. Hi Yuan, you can share your screen and go ahead, present your work.
Oh, I'm sorry. Now can you hear me?
Yeah, sure. We can hear you.
Okay. Hello everyone. I'm Duoyuan coming from Tianjin University, and I'm very proud to have this opportunity to introduce our work, knowledge graph-based sensitive filter selection for Android malware classification. First, let's look at these two pictures from McAfee Mobile Threat Report. The pictures respectively show the number of newly discovered Android malware in 2019 and 2020. We can find the sharp increase of malware. So we think group malware with common behavior into malware families, studying such families in an effective way to battle them. Further, we can formulate these tasks as a multi-class classification problem. That is, the malware applications are represented as a one-hot filter vector after reverse engineering, and then they are sent into a machine learning classifier for training and testing. But in such a situation, when we often use permissions and Android APIs as the sensitive filters for classification tasks. But there is a key issue, that is how to select these APIs as a sensitive filter. When we browse the Google developer, we can find a large numbers of packages, classes, and methods. The Google developer provides a bulk of APIs for Android developers to help them successfully complete their development tasks, but it brings much more difficulty for our researchers. After we crawled the data of the official API documentation from Google developer, we totally obtained of 9,238 classes, 167 permissions, and about 80,000 APIs. Obviously, it is unrealistic to use all of these as filters. We need to filter and reduce them. But it may cost a lot of time by using manually way to do this. So to solve this problem, we pay attention to the Android permission. For permissions, the official document gave 3 basic categories. They are normal, signature, and dangerous. For the naming, we can see that the dangerous permission is worthy of attention. And a section of the official document that describes dangerous permissions as follows: is a high risk permission that would give a requesting application access to private user data or control over the device that can negatively impact the user. Because this type of permission introduce potential risk, the system may not automatically grant it to the requesting application. For example, any dangerous permissions requested by an application may be displayed to the user and require confirmation before proceeding, or some other approach may be taken to avoid the user automatically allowing the use of such facilities. So from this, we can see the impact of dangerous permission. So we decided to start with it and filter the appropriate APIs, taking into account the structural characteristics of web data and the research work of predecessors. We have introduced a knowledge graph to help us organize and analyze APIs and their relations. And this is our plans. It contains 3 steps. Step 1, we build a knowledge graph, API permission of step 1, we use the crawler script to obtain API related data from the official Android documents and build a knowledge graph. And here we use the Neo4j as the graph database. And for step 2, we start from the dangerous permission and find the API which are directly or indirectly related to these permissions and use them as a sensitive API list. And step 3, we use these APIs as filter to classify Android malware and observe the classification results to determine whether these filters are suitable for classification. And this is part of the API permission knowledge graph. And different nodes with different relations they have different color. And these are our 4 research questions. And next I will introduce them. So for the question 1, so we hope to use those APIs directly to the dangerous permissions as filters to test its possibility for classification of Android malware families. Here, the directly means that these APIs indicate the requirement for certain dangerous permission. Because using this API is obviously more risky. And the picture shows the classification on 3 data sets. The data sets we use the genome driven and AMD data sets. And the results shows the overall classification effect on the 3 data sets. It seems that the performance is good and the results of the experiment prove that it is appropriate to use such APIs and permissions as a filter. However, the classification results are still not as good as expected. Perhaps just using APIs directly related to dangerous permission is not enough in number. Therefore, in RQ2, we hope to pass through the relationship of the graph and find more APIs that are indirectly related to dangerous permission as filters. Indirectly here, we means that these APIs do not ask for dangerous permission, but they have a relationship with the permission we found in RQ1. And this makes them equally risky. So here we add the API obtained from each relationship transfer to the sensitive API list in RQ1. For each relationship transfer, we expand the API list with the newly obtained API and perform classification experiments to observe the classification effect each time. And the figure shows the classification results obtained by each relationship transfer on the 3 data sets. It can be seen that each time new APIs are added as filters to train the model, the classification results have been further improved. The classification effects on the 3 data sets all show a clear upward trend, especially in 1 to 2 and 2 to 3. When it reaches the 4th time, the overall accuracy is already high. The benefits of expanding the list of sensitive APIs are not obvious. So after we added the indirectly APIs, we still have another questions. So whether we can find the discovered, undiscovered hidden sensitive APIs, which means it doesn't have any relations with the API we have found in RQ1 and RQ2, but they may have the similarity functional descriptions in the official documentation. So here, we tried to compare the functional description similarity between those undiscovered APIs and the discovered APIs. And we further expanded the list of the sensitive APIs by this way. And the picture shows the comparison between the classification result and the RQ2 result using the expanded sensitive API list as the filter. It can be seen that in the 3 data sets in each link, the API based on the similarity of function description is used to obtain a better classification result. We can compare the similarity of functional description part of the API to discover the APIs in the graph that can be found through a hyperlink. And these APIs can also improve the malware classification results to a certain extent. And in addition, Android permissions are also organized into permission groups, and permissions with the same group are granted synchronously. For example, when write contacts, this permission is authorized. App also has read contacts permission. So similarity, we want to observe the help of different permission groups and their related APIs in order to classify malware from the perspective of permission groups. The picture shows the classification results of different permission groups and related APIs as filter. Among them, the location, phone, and storage permission group perform better than others. As can be seen from their names, they are more closely related to private information, and APIs related to this type of permission group should be paid more attention to. And the permission in group microphone performs worse. Maybe they are not much related to private content, and the number of APIs related to it is very small. Therefore, we can pay less attention to these APIs in practice. In this paper, we conduct extensive experiments for selecting APIs which are better for Android malware family prediction as filters to filter out suitable APIs as filters. We built an API knowledge graph and selected APIs related to dangerous permissions for malware classifications based on the dangerous permission groups required in Android development and the hyperlink relationship in the knowledge graph. And after that, to test the selected API's effectiveness in the classification task, we conducted many experiments based on multiplayer perception. We used the classification results to reflect the role of API as a filter, comparing the F1 value of the classification result using the API we select as a filter for classification has achieved excellent classification effect. Not only that, after adding remote APIs that were finding by comparing the similarity of API function described, the classification results have also been significantly improved. This illustrates the effectiveness of finding an API suitable for malware classification through the dangerous permissions. And meanwhile, we also found that APIs related to 3 dangerous permission groups at foreign location and storage can give more help to the malware classification. That's all. Thank you.
Okay, let's thank the fantastic presentation given by Duoyuan. Now, I have a very simple question about the RQ3. That is, how do you define the functional similarities among APIs?
When we build the API permission graphs, we find the relationship is very the number of the relationship is small. So so we found if the 2 API they can do same things, such as they both have relationship with the message or the phone accounts and so on, but one has a relation with the dangerous permission, but another don't. So we can compare whether they do the same thing or the similarity thing to decide whether they have the same risky.
Okay, then how to determine they are doing the same thing? By their documentation about their functionality, or the parameters or the returned values of their definition.
Okay. We calculate the similarity between the 2 APIs description in official documentations.
Okay, I see. Okay, thank you for your answer.
Okay, thank you.
Thank you, Duoyuan. Okay, now I would like to invite our last speakers, Bakheet of the papers and empirical studies on developing secure mobile health apps, the developer's perspective. Welcome, Bakheet.
Hello.
Hello, Bakheet. We can see your screen now.
Can you guys see my screen now?
Yeah, sure. Very clear. Okay, please go ahead.
Thanks. So hi everyone, I am Bakheet Aljedaani, and I am from CREST, the Center for Research on Engineering Software Technologies Research Group at the University of Adelaide, Australia. Today I will be presenting our work, an empirical study on developing secure mobile health apps, the developer's perspective. This work is a part of my PhD research, and it is co-authored by Aakash Ahmad, Mansoura Zahidi, and Muhammad Ali Babar. So here's the outline of my presentation. I will first introduce the topic. Then I will explain the research objectives and walk you through the adopted research method. And then I will highlight the study findings and threats to validities. And finally, I will conclude the presentation and point out some ideas for extending this work. So currently, millions of mobile apps which are available to download and use to improve our life. Mobile health, or mHealth for short, are among them. In fact, mHealth apps are revolutionizing delivering healthcare services by taking advantage of mobile devices features such as the embedded sensors and mobile computing abilities. Thus, it became a promising technology to provide low-cost efficient and digitized health services. Many studies have proven that mHealth apps can improve the quality of health services in many health scenarios. For example, managing dermatologic care, managing chronic disease, clinical practices, mental well-being, etc. As we can see from the figure here on the right, mHealth apps can be categorized as general health apps, such as patient management apps, or fitness monitoring apps, such as activity tracking apps. Generally speaking, all mobile apps, including mHealth apps, collect, process, store, and transmit user and device data in and out of a device over various networks. Any compromise on the confidentiality, integrity, and availability of data would lead to compromising the devices, would also lead to compromise the device's information, such as locations, activity tracings, and lead to a financial loss. Therefore, security threat should be eliminated and should be considered at the early stage of the development life cycle to prevent any private data leakage or breaches. And therefore, we believe the developers of mHealth apps have a big role to ensure the security, and that's what our paper about. So before explaining the research objectives, we conducted a systematic literature review, SLR, which has been already submitted to a journal to understand what research have been done and what the research gaps can be. So we identified the following research questions that we need to investigate. Research question 1, what challenges do developers face while developing secure mHealth apps? And we collected qualitative and quantitative data for this research question. Research question 2, what practices are used to incorporate security measures in mHealth apps? And we collected only qualitative data for these research questions because we did not want to limit our respondent to a few security practices. For the research question 3, what motivates developers to engineer and develop secure mHealth apps? And we followed the same approach as research question 2. Research question 1. We collected qualitative and quantitative data for this question. So here's a full picture of our methodology. It has 4 phases. I will briefly explain them. For the first phase, as we designed the study protocol and questionnaire. After reviewing the literature, we were able to design our questionnaire, which has 15 questions. It's important for us to involve only mobile health apps developers. So the first 3 questions were screening questions. We asked the respondent to name one mHealth app they have developed, explain how it works, and provide us a link to verify that app. To improve the survey content we conducted a pilot survey with the first 24 respondents to remove any ambiguity and improve the survey. For the phase 2, we invited and engaged participants. We followed 4 approaches. First, we sent email invitation to our close contacts. We received 17 responses. Then we emailed GitHub and Google Play Store developers and received 29 responses. And then we posted our survey questionnaire on social media, and we got 37 responses. And last step, we followed the snowballing technique, and we received 14 responses. Total emails sent or total invitation were sent was about 1,300 emails, and we were lucky to get 97 responses. For the third phase, which is demographic analysis of survey respondent, we ensured that we get representative data by having respondents from different geographic locations, experience, team size, and using different development platform. And last phase is synthesizing and analyzing survey data. We use this descriptive statistics to present the result of the closed-ended questions, such as Likert scale questions. We use thematic analysis to present the open-ended questions. Particularly, we used in vivo software to organize and review our generated codes. So now I will move on to our findings. For research question 1, as I indicated earlier, we used a Likert scale question to rate the respondent agreement on 8 critical security challenges, which we have identified from the literature review. This question is followed by an open-ended question to allow respondent to mention any other challenges. Therefore, we identified 10 critical security challenges. The top 3 which have received the highest agreements are little or no budget for employing security, received 85% agreement. Insufficient security knowledge by the developers, received 80% agreement. And lack of security testing for mHealth apps, received 75% agreement. Our respondent also pointed out that they have difficulties in dealing with legal applications, policies, and procedures. Further, they have found it is difficult to maintain mHealth apps and data. For research question 2, which investigate the security practices, we used only open-ended question to allow respondents to share their knowledge. So we used Microsoft Secure Software development process to classify the obtained responses. We identified the security practices based on their appearance in the software development lifecycle. For example, Microsoft Secure Software development process has 5 phases, and we identified some practices. For example, in the requirement engineering, respondent indicated that they prioritize security requirements. For software design phase, respondent mentioned that they use security guidelines as a practice to ensure the security. For phase 3 software implementation, respondent indicated that they use secure code analysis. And for software verification, a respondent indicated that they used attack simulation as a practice to ensure the security. And software development phase, respondent indicated that they use app security reviews to ensure the security. Interestingly, a view of our respondent indicated that they have not incorporated any security approach during the the apps they have been developing. And for the last research question, we collected qualitative and quantitative data using the same approach as we followed in research question 1. So we identified 10 security motivational factors. The top 3 that have received the highest agreement among our respondents were insecure mHealth apps have a bad consequences, received 85% agreement. Maintaining the vision and reputation of organization received 81% agreement. And seeking career path and promotion received 71% agreement. For the open-ended question, our respondent indicated that they were motivated by the practices for ensuring security by their organizations. And they also consider reducing the cost of maintaining the app as a motivation factor for them. To conclude the presentation, we investigated the developers of mHealth apps' views on the security challenges, security practices, and the motivational factors. We believe our finding can be helpful for researchers and practitioners with evidence-based knowledge to develop secure mHealth apps. However, our study might got affected by some threats. We believe the sample size can affect the generalization of the study. We also believe that we have not achieved data triangulation because we only obtain data from one source, which is survey. And we believe that our study might get affected by multiple responses by the same respondent because we provided a $10 gift card for those who provided us a valid response. So developers who develop more than one mHealth apps, they might participate in our study. For future work, we believe this study can be further extended by focusing on the security challenges from the user's views. We also believe it would be possible to investigate the impact of the identified security practices. And last but not least, we believe it would be possible to further explore the motivational factors to understand how it can enhance the security, such as the role of security leaders. We acknowledge the participants who involved in this study. This research is partially supported by the Cybersecurity Cooperative Research Center. And we thank CRIS team members for improving the manuscript of our study. Thank you. Any questions, or feel free to email me at this email address.
Well, thanks, Bakheet, for the great presentation here. I have two simple questions about the study. The first one is that how many responses are from the same respondents among the total 97 responses?
We were not sure because each respondent gave us like different email address, different mobile apps they have developed. So we are not sure, but we have seen some developers who have developed 8 mobile apps, health apps. So we are not sure about that.
Okay, so you do not have their true identity, so you cannot get how many responses are there from same respondents, right?
Yep.
Okay, and then my second question is about What are the major takeaways or lessons that we can learn from this study?
This can help the organizations who are developing mobile health apps to pay attention for the security and especially the challenges. Try to ensure that the developers have the right security knowledge, using the right APIs, using the right libraries that has like the right tools to improve such a mobile apps that hold sensitive health data.
Okay, I got it. Okay, thanks Bakheet again for the presentation and your answers.
No problem.
Okay, this is the end of these sections. Thanks to all the speakers and audience. Yeah, thank you.
All right, thanks. I think that's the end of today's sessions. Please be reminded that tomorrow we'll start at 11 a.m. Singapore time. And in the end, thanks again, Dr. Guo, for hosting the session.
Okay, then goodbye.
See you tomorrow.